the most important thing for this talk is that I've been hacking away on inline for months and months now, and so I have a bunch to share. There's a few other tidbits here. Another important note is Daniel Spiewak is giving a talk at the same time as me, and we have a little competition going. So whoever gets the most people in their talk to tweet the hashtag basically wins bragging rights over the other person. So if everyone could quick throw out a Twitter tweet of Spiewak for duck types, that'd be amazing. Thank you. All right. Let's go through an agenda of what we're going to be looking at. We're going to be looking at a quick history of the Macrolution in Scala 2. That would be how macros evolved, what they did, and how everyone started using them. Next, you all know that Scala is going to 11 this year. So there's a whole bunch of new features, whole bunch of cool stuff. We've been kind of experimenting with it. So we're going to cover inline and deriving. And the goal of this talk is that you can actually make use of them at the end of the talk. I am talking fast because there's a good bit of detailed content to get through. And we're going to be focused on practical usage, how to actually get good error messages and when not to use the feature, which is probably going to be about 80% of the time to 99% of the time, depending on who you are. Okay, cool. Let's look at evolution of Scala 2.10 and what we learned from macros. So to start off with, Scala 2.10, I was the release manager at the time. We thought that we would release macros as this experimental feature, right? We're going to put this experimental tag. No one will adopt it in like wholesale fashion because it's too experimental. It's only going to be for advanced use cases. We're going to get to learn kind of like where this is meant to be used and what's supposed to happen, and kind of evolve it as we go. What happened was everybody tried it. It got adopted everywhere. And it was so applicable and so helpful to the community that basically all of the assumptions around how to fix it long-term disappeared, and it had to be maintained in as stable a possible way as you could do. So I collected some actual user quotes around macros, just so you know that they were kind of like came out the gate pretty strong, right? Scala macros look like a low-level hackish solution in search of a problem. Oh, thanks, Ivan. Whereas at the time I was like, oh, hey, neat. These look really cool. Jay Krebs wrote a "Oh God, why?" And this was a blog post about why didn't Scala developers build anything else besides macros? Why did we spend time on macros? A whole bunch of fun assumptions in that one. Later on, we get to more modern, quotes about macros where someone says, I encourage everyone to go out and explore the possibilities of applying it in our own projects. This is Walmart Global Tech blog article, which is kind of cool. So like, if you go from, oh God, why to I encourage everyone to try them, we actually made a good bit of progress. But they're still painful. It's fine. Like everybody loves the API, right? I threw together a quick survey of basically how macros are getting used and tried to throw it in a Venn diagram across various libraries. The point of this is it is complex. There's like a crap ton of things. We asked ourselves on the language committee, what are the use cases for macros? And no one could ever give a good answer to it. And I think this is why, is they're used everywhere and they're used for so much. And so what language features do you add to kind of limit macros or make macros better or safer or more sane for mortals, right? In any case, let's collect some of the most important things that we saw from macros in Scala 2.10. One of the most important things we saw was basically compile time execution. I can get error messages earlier. I can do optimizations of code. I can get rid of boilerplate. I can have better types, all of the above. The second thing that was, I think, really critical to why macros got adopted was you had no external dependencies. A lot of other languages will use code gen tools like protocol buffers, right? There's this common theme now in say people who use like Ruby or Python tools to throw everything into Docker and then just force people to install Docker. Like I don't want to install another virtual machine to like get my build to work on my machine, right? So if I have Scala working, I can do code gen. Cool. That was a big reason to it. But obviously there's a lot of problems with macros, right? It was hard to do, hard to understand. So I'm just going to motivate why we have a Macrolution coming in Scala 3. And I call it a Macrolution because effectively I tried to take some Scala 2 hobby projects I had in the early Scala 3 days, move them into Scala 3 and see how powerful the new macros are, because I heard macros are going away. They're only going to be, black box, all this kind of stuff. And it turns out that I was able to cut my macros in half or more through other language features. And in many cases, you don't even need macros anymore because the language does things it didn't do. So let's continue. First of all, how do I start with Scala 3? Well, SBT new, awesome. Thank you so much, whoever did this. I actually know who it is, but you just do an SBT new project with a no macros, okay? That's the name of your project, and then we can get started. My first Scala 3 program, for those of you who haven't written Scala 3, you just annotate a method kind of written out in space in a file. You make a file called hello.scala. You make a main method called run, and you can println hello world, and it works. Isn't that wonderful? Man, the number of times I've seen hello world, it's like 3,000 lines of code, whatever. Anyway, first Scala 3. Your second Scala 3. Obviously, the most important thing to do is to calculate the byte size, how many bytes various things in memory take, because I've been writing a lot of C++ for work, and oh man, like I can bring it into Scala now. So I can say, what's the size of a type? And I can actually pattern match over the types and like figure out the size and say, yay, I missed C++. Thank you, Scala, for bringing it back. Yeah, this would be the second thing you write, right? Anyway, we're going to dive into this. We're going to look at how to do this ourselves and like why this matters, when it matters, things we can do with it. This should look funky and different, but we're going to step through each piece of this slowly over the course of this talk. So first of all, I think you saw in this slide, I am doing things at compile time, not at runtime. And previously, to accomplish that bit of code that you saw, I would have had to use a macro. I would have had to look at types in a macro. I'd have to look at syntax trees, and I have to synthesize code expressions. And I don't have to do that anymore with inline. Inline gives me a facility to do it within the context of Scala syntax and kind of a little bit better in terms of how it works. So let's do a simple example of what inline looks like, right? Let's say, I think you probably have seen this before in some slides. If not, hopefully it's good. I want to make an assert method, okay? So I want to create an assert method that's conditional and expression and says, if this condition is true, alert. And I can actually define this inline, which means when I call it, it's going to replace that call with a compressed version of the code, right? It's going to look at that conditional and say, I know that this is true, right, when I'm inlining, and I can actually erase the if expression and just put the println. If I put false there, this would erase down to just the unit expression. So that's kind of cool. We have this like facility now that is guaranteed to run. Unlike in Scala 2, the inline annotation was not guaranteed to ever work. And this will ensure that I can do some level of erasure and some level of use time compile analysis, right? Kind of cool. A less simple example, right? If I have assert and I have an expression called t and I want it to run twice. So I want to say like, when you assert this condition, if it's true, I just want you to do the expression twice. I don't know why you would do this. This is just a simple example, but let's say assert true, then I want you to println hello world. How many times does hello world get printed? Well, it kind of compiles down to this, you would think, right? If you know Scala. So this particular argument variable is known as a byvalue argument variable. So the way Scala has to encode this in inline is it actually has to kind of assign it to a temporary and pass it into the function. And so you're not passing an expression of println, you're actually passing the value of the result of println, which would be unit. And so you're doing if true, then unit. And this actually gets compiled down to just println hello world once. Okay, because of how everything shrinks. So that's not really what we wanted. We actually wanted to reevaluate this expression more than once. Scala has a standard way to do this that's called by name values, which we could have used. Instead, though, we're going to use a new thing called inline arguments, and we'll get into why a little bit later, or inline parameters, sorry. An inline parameter, I can say that the parameter itself is inline, which means the entire syntax tree needs to remain available for me in the encoded code, and I will kind of blanket place code from A into code to B. So inline means I take this entire syntax tree here, the whole thing, and everywhere it shows up, I'm just going to throw it into the block of code. Hopefully that makes sense. I can't see questions or hands or anything, so if anyone is confused, feel free to like ping on chat. We can go into details. Anyway, effectively, inline lets me lift this whole thing and write it in twice. Inline parameters have call semantics equivalent to by name parameters, but allow for duplication of code in the argument. This is the definition according to the specification if you read like the Dottie documentation. So what this is really saying is if you do a by name argument, what happens is a kind of lambda is lifted in line before calling the argument, right? Before calling your inline method, and then you're actually using this lambda to reevaluate the code more than once. Whereas in this semantics, I'm actually lifting the whole bit of source code and passing it down. So it's kind of a way of passing source code to yourself, which we'll get into. So in Scala 3, we have 3 different parameter types. We have byvalue, where I can evaluate values before a method call, and in the inline sense, right, I will evaluate and then write my code directly leveraging that value. We have by name, which are evaluated every time they're used, and this is done kind of via constructing lambdas or thunks, if you will, that will reevaluate the thing every time you try to reference it. It'll call that function or thunk or whatever. And then we have implicit, which is it has the same semantics as by name, but you're in this implicit zone, which means you have access to the whole syntax tree within inline. And it means you can do a little bit more than you can with by name. And we'll talk about the implicit zone. Let's go to another example. Okay. So let's say I'm trying to make a generic like writer method for writing out bits, because everybody does this, right? Who doesn't love writing binary protocols? So I'm going to write out shorts, but I want to actually allow people to decide if they want big endian or little endian, because that's probably the most useful debate that's ever happened in the course of the internet. So I'm going to provide an enum where I can say you pass in endian. If they want big endian writing, right, then I will write the big part of the integer first. If they want little endian, sorry, I will write the little part of the integer first and the big part second. Wonderful. I'm so glad we have to do this. But if I make this an inline method, what does my output look like, right? Can it erase this and kind of make it so I know that the person said big here and it only inlines the 2 write calls instead of inlining this whole, loops and jumps and matches and that sort of thing? Well, it's not going to work out of the box here because, again, I have those argument semantics of call by value. So effectively what this kind of looks like, and I'm fudging, is it kind of looks like I say the value is 1, the endianness is big, and then write is this particular mechanism. And so I actually inline this whole code directly. Not ideal. Not ideal. Let's use a new inline mechanism. We can actually take the pattern matching statements and inline them to force them to happen at compile time. So what I can do is I can say inline match, which means this inline is guaranteed to get erased. It also means the endianness has to be available at compile time. So in this case, if I say write short with big, right, and I have this semantics where the values get written, you can see it erases the switch statement or the match statement to like look at endian, right, and figure out which one, because it knows at compile time what to do. And this actually gets further simplified. If you were to look at the actual bytecode, you would just see 2 write calls with the appropriate bit shifts and things. So that's pretty cool. It's pretty cool. I can actually inline pattern matches now. And it does mean that this has to be in the inline zone. So welcome to the inline zone. The inline zone is a reality that we've bent and we've twisted Scala so that everything is available at compile time. Do you know the cool things you can do in the inline zone? This is one of my favorites. I can actually do computations at the type system. If I import my integer operations, the types for them, I can say the answer to life is 1 plus the type 10 to the 1 times 2, right? These are all types. Doesn't this make everyone else so happy? Like, look at this, man. I can calculate things that I have to actually calculate myself to get this to compile. If I were to put the number 40 here, this would be a compile time error that answer to life has to be the value 41. It has to. Like, we know it. It's in the compile time sense, right? Beautiful. We can have these inline matches where we say, if I have a constant expression where the compiler knows the value, I can have case statements that evaluate in the compiler. I can also do the same with if statements, inline ifs, right? So I can now write logic in the compiler. For those of you who have done type gymnastics in Scala previously, you had to write this via weird implicit lookup rules, because we found out that implicit lookups could be turned into a Turing machine where you could look up different values of implicits and get different types out. And so we do all sorts of mental gymnastics to kind of get the compiler to do this stuff via implicit lookup mechanism. Similarly, for those of you who know C++, they do this crazy stuff with template partial specialization because, you know, the compiler doesn't give it to them. And if you want to do something advanced with types, you know, do it as convoluted as possible. Here, it's actually, you can read the code. You can understand what's going on because it looks and acts just like Scala, because it is. All right, in the inline zone, we have a limited subset of Scala, the portion of Scala which can actually be computed at compile time. So we can make inline methods, we can make inline arguments or parameters, as you saw. We can do inline if statements, we can do inline match statements. There's a few magic methods that are actually also done inline. So there's this compile time thing, which is the next bit of the talk we'll step through. There's a thing called transparent we'll kind of touch on. I don't expect most people to need transparent. That's like the 20% of the inline 80% case is transparent. And then there's this notion of reflection in quotes is what macros are now called. And you can, in the inline zone, macros live as like this specialized subset of inline. So it's pretty fun. We're going to walk through these magic methods because these give us the power to actually do useful things and not have inline just be a toy around how to, you know, calculate sizes of bits and some C++ fun. Okay, first of all, you saw that size of method. Let's try to understand that a little deeper. Compile time erased value basically gives you a way of matching on types. Okay, so if I were to write an inline match with an erased value of t, I can have a match statement that works based on types the way Scala would expect. But since this is an erased value, I can never look at the value because I don't have one. Okay, size of is called with a type. There's no value. There is absolutely no value that this could generate. And in Scala, we don't have implicit values for every possible type. You only have like default values for any values, right? Like bytes, shorts, floats. The things I've listed here actually have default values, but objects don't. You can't just random instantiate some object or case class someone has and not give it value, right? So erased value has no value. You can't look at it. You can only do these type matches on it. That's the most important thing. But what's cool is I can have different behavior inlined now. So when I call the size of int, the compiler just automatically turns that into 4, right? And we'll look at why that's cool more. Another fun thing with this is inline can be recursive. So if I want to calculate the length of a tuple, right, I can say, grab me that erased value and I want a pattern match on the tuple case. Again, in Scala 3, tuples are like lists, right? I can do head-tail decomposition. That's what this operator is. It gives me the head of a tuple and then all the remaining types of a tuple, okay? So I can say the length of a tuple is 1 plus the length of the tail when I get a decomposable tuple. And tuples don't have a nil, they have an empty tuple, but that's basically like, I have a tuple with no values in it. That length will be 0. And so then if I try to say, what's the length of int string, guess what? It returns 2. If I were to say int string double, it would return 3, right? Because it does this calculation, but it does it all at compile time. The only thing that at runtime you would see is actually 2. All right, another fun thing that you can do is this notion of constant value. In Scala 3, we now have literal types. So you have literals in a language, right? I can write, I can write the literal hi, which is a string literal, okay? And the compiler has to understand that this is a string literal and turn it into the string hi at runtime. But the compiler actually knows exactly what that literal is, and it's been lifted into the type system. So I can write something with a type of hi or type of 1, and then this gives me the ability to get back the value from the type. So if I know that that's a little confusing, let's look at this in more detail. I can define a type X, which is exactly the tuple of the string hi, the string u, and the string folk. Okay, so that's my type. It's the tuple hi, u, folk. If I try to assign to this type hi, Scala, love, it's going to say, oh man, you gave me the string Scala, but I wanted the string u because that's what this type is here. Okay, so effectively for literal types, almost all literal types, not functions, but almost all other literal types, you can lift that literal type into a value. And you can have that value be a type, or you can have it be a value. You can go back and forth. They are indistinguishable now in the compiler, which is cool. There's no special weirdness we have to do to kind of get this behavior. Why does this matter? Why do we care? Most of you will say, well, I don't really care. Except we'll get to it in a second with deriving type classes. First, we got to do one more thing, which is kind of important. This is called summon. All right. If you're familiar with implicits from Scala 2 and how they've gotten renamed in Scala 3, we now call them givens. Okay, it's a given system. Instead of having an implicit value, we have a given value. Like there's something available at compile time that fulfills this type requirement. Okay, there is a new inline method called summon from, which will summon givens from your use site. So wherever someone calls this print, right, that in that particular context, we will look for a show instance in the implicit or given scope, depending on how you want to talk about it. And if we find one, we're going to call this tc.show. If we don't find an implicit, we can still take a behavior here, which is kind of cool, right? So I can look for something in implicit scope magically, and if I find it, I do something. If I don't find it, I do something else. Previously in Scala 2, if you wanted to do behavior like this, you had to completely do it in the implicit scope. You had to make it wrappers to make it happen. It was a huge pain in the butt. Put simply, if you're making any API that uses type classes, this little technique here can really help you make your error messages not terrible and can really, really, really help kind of iron out some of the weird use cases that you might have with implicit lookup. It is, in my opinion, the best thing to solve some implicit issues in all of Scala 3. How do we get those good error messages? Well, this is fun. There's a thing called compiletime.error that we can call, and it will issue an error at compile time at the line of code you're looking at, and that's going to show up in your IntelliJ or in your Visual Studio, depending on which one you use. I use Visual Studio, so I apologize to everyone who hates Microsoft, I guess. I don't know. In any case, so here we can define that size of method we had, and if we get any type that we don't recognize, right, we just say unable to determine the size of it, and that's kind of cool. So they're going to see they called size of some type, and we'll say we were unable to determine the size of it. Beautiful error message. We can tell the user where it is if we have an argument. So let's say we have a method that has more than one argument. In this case, we just have one because I wanted to fit it on a slide. okay? And I do one of these matches, and I'm matching on a particular argument type, and that argument's the problem. I can actually use this compile time code of combinator to give myself the position and code where this is, and then this error is going to kind of report against that argument so that the user is going to get an error message closer to where they inlined, right? Now, I have not shown you a single macro, right? I have not shown you any kind of syntax tree manipulation yet. This is all just built-in methods in the inline zone. Now, I mentioned I was going to, that there's this thing called transparent. We're going to just talk about it for a brief second, which is, in addition to inline, there's a crazier method called transparent that I can use to completely derive my runtime type at compile time. So in this case, while I said this is transparent def wow that returns any, this method can only return the string high or the number 5, right? If I say wow with true, it's going to be a string, and this is going to compile time check just fine, because it's going to defer checking this type until after it's computed this sucker. These things are a little bit magical. We're not going to go too deep into them. If you need them, cool. Tell me your use case, because I'm really curious how often they show up. Okay, let's get into the real meat of why inline. There's this new thing called deriving. It's a way that we can do combinations of classes and kind of synthesizing classes at runtime in a way that's elegant, that is maintainable, and that doesn't require a ridiculous amount of extra tooling or baggage. So in Scala, there's this thing called derives now. So when I have a case class, I can say, I want this case class to derive the equals type trait. I want it to derive serialization, and I want it to derive some magic, because I wrote a magic class, and that should be magical, right? What the compiler actually does with this is, when it synthesizes your companion class, right, it calls equals.derived. There's a method that is assumed to exist on the companion object of a type class around how to derive instances of that type class for folks. So folks using case classes, folks using enums, folks using sealed traits, they can derive the type class directly without having to write so much boilerplate. This should, in my opinion, for a lot of the like Scala Z, Zio, those kinds of use cases, this should dramatically reduce the boilerplate and kind of get rid of the need for a lot of really, really, really nitty-gritty macros. So this is beautiful, but how do we do it? Okay, so we have this Scala deriving package that gives us access to the actual structure of the case classes and the sealed traits in Scala. And it's done in a way where the compiler makes sure this information is consistent, it's always available, and it's pretty accurate. I actually haven't been able to make it be inaccurate. I've just been able to add type annotations that I can no longer see. So we'll talk about that in a second. So here's an example where I want to grab all of the field names at runtime for a particular class of type T, right? So I want to return a list of strings for type T. I'm going to summon this thing called a product.mirrorOf. Okay. Some of the names of these are a little funky, and I recommend looking at the documentation if you want to get more information about what this means. Product equals case class. Sum equals enum or sealed trait. That's all you need to know for now. Okay, so I have this product mirror of. Mirror of is a type level instrumentation compiler feature that gives me access to types that tell me about the class. For example, there's this mirrored element labels type. It is one of these tuples of string literals. Okay, do you remember the string literals that I had with hello you guys and hello you folk and hello Scala love? Well, in this case, I can actually grab those string literals, use callbyvalue to pull them apart. And if I have a case class called test with X and Y, and I call this field names on it, I am going to slowly rip apart those string literals and turn them into actual runtime instances of the string name. Beautiful, right? Like I can get reflective access to this sucker effectively at compile time. Very, very, very cool. Right, I'm going to leave that on for a second so people can digest. And we're moving on. Okay, the next thing I need after I have this deriving runtime access to everything is I need a combinator API. So, right, I'm going to create a simple type class called like my behavior. In some cases that I'm going to show you of stuff that I've done, I did a lot of serialization. Like this is really, really, really good for deriving serialization. I think it's one of the prime use cases for it. But you can also do a lot of these functional kind of type classes associated with various, equals and functors and that kind of thing. Anyway, the key is you need a way to compose yourself from tuples, or if you want product types. So I need a way of taking my behavior A, my behavior B, and getting a my behavior of A and B, right? I need to figure out how to handle my base classes. So if I have a sealed trait A, case class B extends A, case class C extends A, I need a way to take B and C and create my behavior of A. Or if you're cool Scala-y, you can say B or C. Fun, right? But I need this way of like composing my things together, and then I can start doing type class derivation. Not every type class actually can automatically do this, so it only applies to some. Let's talk about some early lessons of using inline. We don't have a whole ton of time, so sorry that I rushed through a lot of these slides. So I've been using inline pretty heavy for 2 use cases to try to tease out all the issues, and we've been building these up for about a year and change now. One is I've been doing this shady side project. It's on my GitHub. It is an OpenGL shader DSL where you write all your code in Scala, and a portion of it gets recompiled into OpenGL shader language and sent to the GPU. And then your transitions from Scala to OpenGL are kind of inferred for you. And we figure out how to shove bytes into the GPU on your behalf. This is not CUDA. This is actually just straight up OpenGL, and you'll see how terrible my actual graphic skills are in this project. The other one is sauerkraut, which is kind of the evolution of Scala pickling. It synthesizes serializers with a composable format output. So right now it supports protocol buffers, XML, JSON, NBT, which is a Minecraft format if you're a gaming nerd. I think there's one other that I'm missing. But yeah, also the protocol buffer support is from scratch. It's not, it doesn't rely on the library. It only relies on the library to do like backward forward compatibility checking. In any case, what we learned from these 2 projects, right? The reason I wanted to highlight them is to show you we've done some sophisticated kind of teasing at the edges of this and some weird use cases. Scala Inline actually, specifically for shady side, I had a Scala 2 implementation. And over time, I was able to erode the size of my macros down to a single macro that does the Scala to OpenGL shader language conversion, syntax tree to syntax tree. And all the peripheral stuff around that kind of slowly got moved into inline mechanisms. So I was actually really happy with the reduction in the size and shape of the macro to truly a use case that needs a macro, and only that one. The one really nice thing that we saw was this looks and feels like Scala 3. You write Scala 3, you write this language and code, you look at the code, and you're not like thrown for a loop over what the hell's going on. I can give the users really good error messages with a little bit of investment. It was actually a bit harder to do this in macros. There still is an issue where sometimes inline error messages are explosive. And generally when they are, it's your fault as an inline user. Not like there are ways that you can avoid giving that terrible error message to your users just by being a little careful. The only error message that's still bad is around the amount of recursion you can do with inline. So we'll talk about that in a little bit. Next up, literals, type literals, and evaluation is actually super, super strong, super, super cool. It gives you all the runtime reflection, or sorry, compile time reflection that you needed in Scala in a safe way that is relatively easy and simple to understand and use. it doesn't give you the super crazy advanced stuff. So if you're doing, I'll give you an example for protocol buffer support, right? We actually wanted to annotate types and instances and do like more synthetic class generation. You're not going to get that, right? You're going to get more simple Scala stuff. And that's a good thing. Another thing that we learned here is that tuples in Scala 3 are freaking awesome. They really did a good job fixing tuples. There's a few advanced, like higher kinded use cases if you're trying to do a type match across a whole tuple. It gets a little funky at times to do the compiler gymnastics, but we didn't need to. We just did it for fun and ran into it. The other thing I want to throw out is Scala Inline is not a panacea. Right? It's not like everything's magically better. There's still macros hiding under here. There's still some complexity. There's still a little bit of the compiler showing. But for the most part, as I've been using Scala Inline from, at least I would say from Scala days until now, the improvements every release have been dramatic. And more I can ignore like changes in the compiler, which is cool. So I think we're actually in a really good spot for the 3.0. Let's talk about when not to inline. Primarily, when you don't have benchmarks, don't use inline unless your type gymnastic stuff is all about derived, right? So if you're using inline because you think it's going to make things faster, definitely challenge those assumptions. I can give you, there's some links in the slides, which I'll post on chat for you that kind of cover a lot of the weird stuff that we did. And a lot of experimentation that I did and a lot of benchmarking. And there are a lot of cases where the JVM is going to optimize something way better than if you inline it. Because sometimes when you inline, you end up with a block of code that doesn't look like simple Java. And in the JVM, the more you look like simple Java, the more optimized you are. Also, specifically from JVM 8 to JVM 11, there was a lot of optimization done to lambdas. In 11, that matters. So if you're in 8, doing one of these like inline wrap behavior things actually can matter. In 11, it doesn't at all, and can even be negative. Okay, next up, synthetically generated classes. This is one where I wanted to really highly optimize the shape of the class that I'm synthetically generating in this derived use case. If you need to go past dead simple, you're probably looking at a macro at that point, right? If you need to actually synthesize vals and vars that are correlated with the vals and vars of your case class, hopefully just vals, you will need to write a macro to do that. If you can operate against collections of tuples, if you will, heterogeneous lists, then you're totally fine. If you can erase all of that away, which is probably a good significant portion of code, you're totally fine. So again, the highly optimized use cases probably are still writing a macro. Another thing is if you need inheritance of the thing that you're writing. So if I can't just make all my methods inline and say, oh, cool, this is optimal and awesome. If I have an interface that needs to get extended and I put an inline method in that interface, that inline method can never, ever, ever get overridden or change its behavior. I need to understand the entire system. These are whole world assumptions, right? And then also, if I expect to be able to remove all boxing penalties via inline, then I'm going to run into problems. Basically, inlining can only go so deep, right? I could theoretically, if I was crazy, this was like a C++ thing back in the day, of let's make our entire application be within the template metaprogramming world. And then I write a main method that composes all these weird, template metaprogramming stuff, and it'll compile down to like one line of C++, and I'll be so happy, and it'll take me 5 years to compile the thing, and everything's wonderful. In Scala, you could do the same and say, I'm going to make every single method I write inline so that it's as optimal as possible, and I get this really, really cool, simple main method that's just the little bit of code I want, and everything has like compressed well. No, you can't do that. You could try, but there's a limitation for how many inline stacks you can go down before the compiler says this is too much. It's going to take too long, right? And remember that there's a compile time overhead to using inline. It's not very high. It's it's still really snappy, but there is an overhead and there's limits, right? We can't just use this everywhere. All right, so I have some extras for you. I'm just going to highlight these and you can take a look at the slides later. There is, if you want to actually define error messages that have type names in them, you can do so, but you have to write a macro. This is what a macro looks like in the new world. Yeah, man, it's tough, right? Look at that. Also, if you want to know some Scala 3 examples from these two projects that we've been hammering on, Shady Side uses inline. There's some derivation examples, some macro examples, some opaque type examples if you want to see them. For Sauerkraut, there's a lot of inline. We actually, the stuff I was showing about how to do big little endian is actually completely available in here. If you want to do big little endian encoding with UTF-8 reading and writing with var-ints from protocol buffers, it's all there. It's available. It's inlined. I don't know if it's great that it's inline, but it is, and the performance is either negligible or a small win. We do some derivation, and we do a little bit of macro-ish. We're actually proto descriptor. If I were to show you this, we are annotating types, and we're extracting the integer values of those annotations. And we had to use a macro for this. We couldn't do it in straight inline, but they're not super large macros, and it's still pretty cool stuff.